Right. Let us start perhaps. So this is the last talk for this week. Now there's going to be some activity next week. So first of all, we will have, as you probably know, 2 talks on Tuesday next week. Sorry?
What will be the talks?
So 2 o'clock and 3 o'clock. 2 o'clock it will be Boris Horuzhenko's talk about something that is actually close to the dual program as well. So it will be some. Okay, don't. I mean it's written on the screen, and I think the abstract is there. And the other talk will be. Do you remember, Marcello? You know everything.
Probably website.
Grisha Rosenblum. He will be talking about something related to periodic. So it will be spectral theory for various periodic structures, but not always periodic. Okay, I think it will be interesting for, despite the fact that it's not all of it is about periodic. Now, there is, in the email that you have received, there is announced a talk for Wednesday, but I think it probably will be cancelled because the person, the circumstances of the person have changed, so he probably will be able to give a talk on Wednesday, but on Thursday, we plan unofficial. It will be not widely advertised, so I will just tell you. So Ilya Kachkovsky, who is here, he will give a 2-hour survey of works by Burgay, Goldstein, Schlag, and Burgay about multidimensional discrete Schrödinger operators and localization, Anderson localization for that. So he will just describe the results of the methods. It's actually, there are 2 papers, Burgay, Goldstein, Schlag for 2-dimensional results, and Burgay for higher than 2-dimensional, and I think Ilya will mostly be talking about Burgay paper and so on. And he will go into some technical details, so it will be basically, unless you are really interested in detailed things of stuff, part of what's going on, then you might want to skip it. And it will be, well, I don't know. Ilya, how technical it would be? I just.
Okay, so I will probably not do like the technical rules. I'll just explain
The ideas behind them.
the ideas and what kind of technique is used to prove, not the actual steps of the proof.
Okay, so maybe it might be not that scary. So maybe you. Okay, anyway, it will be on Thursday. We plan it for 11 until 1 o'clock, so it's next Thursday. And it will be in seminar room 1. So not in this one, it will be in the big seminar room because this one has been booked by the dual program. Right, and I think that's at the moment that's it for the next week, but if we can reschedule the talk on Wednesday for the other day, I will let you know on Tuesday during the talks, Tuesday talks. Yeah, I think that's all the announcement. Yeah, so Boris is here, so he can, there was a question what we will be talking about next week, so.
It's a nonlinear analog of May-Wigner instability transition.
Does not say. Okay, right. Yeah,
it's counting points of equilibrium from the nonlinear dynamical systems.
Okay, yeah, so you will explain us in more details what it is. Right, anyway, so today it is taught by Reimer Kuehn from not King's College Cambridge, King's College London, and he will talk about spectral sample auto-covariance matrices, and there is some talk with type
Yes, exactly. Okay. Well, not actually well hidden. It comes fairly early. So, thank you. Big thanks to the organizers for giving me this opportunity to present this result here. It's a bit dated already, but there are open problems, and I hope that some of you might have some ideas on this. I should also give a health warning. This will not be rigorous to the degree that you might be used to. So this is definitely a physics kind talk, so bear with me. So this is the structure of the talk. I will describe the problem, sample autocovariance matrices, and what I'm interested in is actually the spectra of those. And there is a there's a closely related problem, the Vichat-Laguerre ensemble, which is much researched. The spectral problem has been solved in the 1960s by Marchenko and Pastur, and there are tons of papers and generalizations on this problem. Whereas for the sample autocovariance matrix problem, there is in fact very little. I will describe my main result first, and that is a scaling formula for the spectrum. It comes out of a calculation, not of mathematics. And it suggests that it is a generalization of Segue's result for spectral densities of Toeplitz matrices to a case where we have sampling noise. So it has the same structure as Segue's integral representation for the spectral density of Toeplitz matrices, and that's where the Toeplitz matrices appear. And I will discuss the result and its relations, and then we'll go a bit through the calculations. Since it requires approximations, some of which actually not well controlled, we have to worry how good it actually is, and I will tell you about the tests. This is the plan. So let's look at sample autocovariance matrices. We assume that we have a stochastic process, so a sequence of random variables. And then we take a realization, little xi, and I define my autocovariance matrix in this form. That's an unusual way of doing it, by the way. Many people, if they know that the sequence is second-order stationary, would formulate it actually not in this symmetric way, but rather write it. Maybe I should. Popular other measures would be Cij is 1 over m, sum over I, x, sum over t, xt plus I minus j. So write it directly as a random Toeplitz matrix. Whereas the way I write it down is a much more symmetric way, and it's actually part of the things that we had to do in order to.
You have to bring it down a little bit.
Fully. That was necessary and actually to carry through with the analysis. So there's a formal way. If I define this matrix capital X with matrix entries xit, which is xi plus t, so capital X is a rectangular Hankel matrix, then I can write this object as the x times x transpose, the ij element of that. And then if you look at this expression, what you expect for large M, that this converges to in the limit m to infinity to the expectation value, which I described with angular brackets here, and we will expect 1 over square root m fluctuations. And I'm assuming that the sample size is comparable to the number of time lags I'm interested in, and we will take both to infinity. So in essence, what we find is that this sample autocovariance matrix, it's symmetric by construction, and it's not itself a Toeplitz matrix, but there's a randomly perturbed Toeplitz matrix. I'm interested in the spectrum of that. And I'm also actually interested in the spectrum of this if the x, this time series is not a series of IID variables. I want it to be sort of have some dynamical correlations, and I'm interested in the fact of the correlations. Let's look at the related. First, let's discuss the spectrum. I'm interested in the spectrum of C as the sample size goes to infinity, and the number of time lags I consider goes to infinity. And if we look back to the related problem of sample covariance matrices, we expect that the result will depend on this aspect ratio n over m. That is rarely discussed. Non-aspect ratio different from 1 is rarely discussed in the autocovariance matrix context, even MATLAB only has the alpha equals 1 thing implemented for the covariance matrix. So people are much fixated on the quadratic case. So this is our expectation, and it will turn out that this is true. So we take the limit n to infinity, m to infinity at fixed alpha. So what do we know about this problem? Not much, actually. There's an existence proof for the case where the stochastic process is a moving average process with white noise driving. That's by Bazak, Bose, and Sen in 2011. And they do this, in fact, as most other people do, at aspect ratio 1. Then, actually, a year earlier, published some numerical studies where he showed that it is independent of the nature of this precise nature of the driving, as long as it is zero mean and has a certain variance, which is assumed to be finite.
Reimer, what do you assume on underlying stochastic process? X. Gaussian?
No, not necessarily Gaussian. I'm taking a sample.
But with kind of correlations.
With correlations. We are interested, actually, I'm interested in the case with correlations, yes.
But should it be ergodic or mixing?
I want it to be second order stationary, and I want true autocovariance functions to decay sufficiently fast as a function of time lag for the autocovariance function to be an L1, so absolutely summable. That's what I require.
And one more question. So when you say alpha is fixed,
Yes.
so if, we're in different regimes, say m equals n squared or n equals m squared, are you saying that this is uninteresting or not?
No, actually, if you have m equals n squared and take the limit to infinity, then you are in the alpha equals 0 limit, effectively, in the...
Okay, so you don't exclude alpha 0 or infinity.
I don't exclude alpha 0. Actually, I'm coming to alpha 0.
Okay.
Alpha 0. So one other result related, random tuplets, Hanke and Markov matrices were considered by Bridge, Dembo, and Jiang, and they showed that the limiting spectral densities exist and are with probability 1 independent of the realization. So what we know something in the alpha equals 0 limit. Then we have a tuplets matrix in the alpha equals 0 limit. For a stationary process, our autocovariance function is a tuplets matrix. And so we have Seger's theorem, and one way to write it down is that the weak limit of the spectral density in the large system limit can be written as this integral, which involves the Fourier transform of the autocovariance function, which is called the symbol in this context.
What do you mean by this limit? You mean
the size
of your matrix is going to infinity?
Alpha goes to, first I take the limit alpha goes to infinity, which means I have infinitely large samples, and then I take the limit n to infinity. And first m to infinity, then n to infinity. That's the alpha equals 0 limit. I could do that possibly taking m as was just suggested, by going to take m equals n squared. That would also move to the alpha equals 0 limit.
And what is the limit?
The limit is this
limit of what? The limit of what?
Alpha is n over m.
Yeah, but what is the limit of each object?
Of the spectral density, the spectral density. Yes, yes. So this is the limit of the spectral density. That's the known result. That's the alpha equals 0 limit. And now let's compare with the closely related Wishart-Laguerre ensemble to see where the problems are and what the differences are. So if you think of the Wishart-Laguerre ensemble, then what you're considering is n-dimensional data, and you measure the covariances of the ith and the jth component of these n-dimensional data, taking m measurements of them. So that's your sample covariance matrix. And in a formal way, you can also express that is in this version xxt, where the matrix X is, however, not a tuplets, not a Hankel matrix in this case, but just a matrix with independent columns. at least independent columns. And just as for the auto-covariance case, you expect finite sample fluctuations around the mean. So this, for finite samples, is a random matrix. That's the famous Wishart-Laguerre matrix, and the spectral problem was at fixed alpha solved by Marchenko and Pastur in the limit n to infinity, m to infinity at fixed alpha. And this law is for the assumption that the x components are all independently identically distributed with zero mean and independent. So that's the case. It was solved, and numerous generalizations with correlations, with certain correlations, have appeared in the literature since then. I think Pastur's paper has more than 700 citations, which is indicative of the importance of this result.
Rama, can I ask a question? So if you
Yes.
compare this with your case,
Yes, I'm going to compare it in the next slide. I'm going to compare it in the next slide. So let's see the principal difference. This is the X matrix in the covariance problem. So in the simplest case, all the matrix elements are IID, zero mean, random variables. If I look at the auto-covariance case, then this matrix is a Hankel matrix where the columns are shifted variants of a single time series. And that's a massive difference. Even if the individual xi's were in IID, independent random variables, there are strong correlations between the columns of this X matrix. And that creates sort of several differences in the most. So first thing, I mean, just a reminder, this is a Hankel matrix. The number of random variables in this problem, which goes into the spectral density for an n by n matrix, is of the order n, whereas in the Wishart-Laguerre ensemble is of the order n squared. So we have n squared random variables to create a distribution of n random eigenvalues. Here, the number of random variables that goes into the spectral density is itself only of the order n. And this creates really the problems in getting to the core of this problem and getting quantitative results. So there's a lot about the Wishart-Laguerre ensemble, and as we've seen, there's very little in the auto-covariance problem, although it's very clear that auto-covariance matrices must be of some interest in signal processing and many applications involving time series.
I remember
Yes.
vaguely that if you consider matrices of this structure, just x's are independent, right?
Not
Could be,
necessarily. Could be.
could
Yes.
be.
Yes.
Then I remember there were some mathematical results on density of such matrices by Miller, I think.
I'm not aware of it.
From the States.
No. There's a paper by a guy in Munich, but that was a bit later, which that looked at blocks of these things which were themselves very far apart. So
No, I have something different, but okay.
okay,
I will.
let's
I will-
yeah, that would be great. So this is the situation, and let me formulate the main result now. This is the result that we have the spectral density. So I assume that the autocovariance is absolutely summable. The spectral density at fixed alpha of this object can be written as an integral which involves the symbol of the true autocovariance in this scaling form. It's the result of a calculation, and we have the calculation actually gives also an expression for the scaling form. It's a logarithmic derivative of a function which is essentially an incomplete gamma function. Okay, never mind. Let's look at, stare at this formula for a while and assume my data were actually IID. Then the Fourier transform is just identically 1. C hat of Q is identically 1, and this entire integral is void. So that what we get is rho alpha of lambda in this case is actually rho 0 of lambda. So our proposed scaling relation tells us the following. If we want the spectral density for an autocovariance, sample autocovariance function for a correlated process, all effects of sampling noise are already contained in the auto-covariance function for a white noise process. And the correlated case is obtained by a simple generalization, by a simple integral over the white noise spectra, which is kind of a cute result. I must say we don't have exact results, but you could, if you want, take a simulation, produce a very precise spectrum for numerical approximation for rho 0, and then you're fine, are able to predict the finite sample effects on your autocovariance spectrum. So this is the node 1. This rho 0 must be associated with the spectrum for autocovariances of IID data. The second thing is Sege's result is actually a special case of our result. If you look at the Sege result again, you can play with delta function arithmetic and write it in this form, with rho 0 actually being the delta function, which is the true alpha equals 0 limit of the spectral density for white noise data. So our case is an alpha not zero generalization where we have proper sampling noise of Sege's result for the case of non-vanishing sampling noise. Sege's theorem is, in some sense, a special case of what we have if sampling noise is absent. So that's the result. Let's look a little bit at how it's obtained. I will basically only explain the main idea, so don't worry about the details. So you all know that you can get the spectral density from the imaginary part of the resolvent, the trace of the resolvent, introducing a small imaginary offset here, which is taken to in the limit epsilon goes to 0 in the end, which I will never write down. Now you can get the inverse of a matrix by a derivative of a logarithm. Okay, and then the trace of the logarithm is the logarithm of the determinant, and then you play with the powers of the determinant. You can get a 1 over the square root of a determinant if you spend yourself a factor -2 in the end. So the upshot of it is, and this was proposed many years ago by Edwards and Jones, you can express this spectral density as a derivative of the expectation value of a logarithm of a complex Gaussian. And being a statistical physicist, this is now my statistical physics system, slightly unusual because it has an imaginary inverse temperature, but temperature is rarely of concern. It's interactions that are of concern, and this is the simplest interaction we can possibly wish for. It's a Gaussian model. So, and we know a lot about Gaussian models. There is a hitch, though. We need to average the logarithm of this interval over the disorder contained in this autocovariance matrix. And the way this is usually done is the replica method, where you express the logarithm of the partition function as a limit n to 0 as 1 over n, the ln. So this average is this limit, as you can convince yourself by doing a small n expansion on the right-hand side. And then for integer n, this is the nth power. So this is the partition function of n identical copies of the system, and you average that. And this is possible.
Tends to 0, tends to 0.
N to 0 in the end, yes. Which is, of course, a tricky thing. In random matrix problems, actually, it turns out that, this is then usually a saddle point problem, and in random matrices, often the high temperature symmetric saddle point. So this is more technical. We can actually do with an annealed approximation in this case. That we know that this annealed approximation works for the Wigner semicircle and also for the Marchenko-Pastur case.
Right, but okay.
It's not
that here is not that many degrees of freedom.
Absolutely right. So this is, if we are far off, we need to check. Okay, and that's definitely on the agenda. It hasn't been done yet. So it's definitely
also just a side comment that you use this way, which is a legitimate way to approach. But you can do it without replicas, you know.
You can use supersymmetry.
Then
Yeah.
there will be no question about the
Yes,
rigor
yes,
of this
yes,
calculation.
yes. We should perhaps sit together and do that calculation using supersymmetric method. So if you insert the definition of this auto-covariance matrix in the way I did, and there the symmetric definition is crucial, I realize that the disorder appears only through these variables zi, which are these sums which involve integration variables. So in effect, I'm doing first the disorder average and then the U integrals. And at fixed U configurations, I have these Z variables. And the scaling is such that these are not too strongly correlated, the scaling is such that we expect these to be Gaussian. They are zero mean, the xi plus t. If they are sufficiently weakly correlated, they will be jointly Gaussian. These variables zi will be jointly Gaussian. I can evaluate their mean over the disorder. The mean is 0. I can evaluate the covariance over the disorder. And the covariance now involves the true auto-covariance function. This is the expected value of xk plus ixl plus j. That's nothing but this object. And what you see here is that this covariance of these Gaussian variables, this matrix Q with elements Qij, is actually a tuplets matrix. It depends only on the difference C of I minus j. So knowing this statistics of the zi, then we see that the zi integral is actually a Gaussian integral, which we can do. And the result is 1 over the square root of a determinant, which you put in the exponent. So the logarithm of the determinant of something, which is a tuplets matrix, and that's sort of what we learned how to do that. We use Zegel's theorem to express these spectral sums here. So I don't need to remind you about this theorem. We had it before. So if we have a tuplets matrix, we will use that. We will use this result to express the logarithm of the determinant. So keeping track of the finite n, finite m approximation, which you need to do. So this integral is basically a sum, a discrete sum of these q mu's, which can be written as in terms of the Fourier transform of the true autocovariance function, and has this structure. And the spacing of these q vectors is 1 over m. So it was an m by m matrix. The spacing of these q vectors is 1 over m. Next thing you do is you enforce this definition of the q values using delta functions and their conjugates. So I can then rewrite this, and I get another Gaussian integral, which I can do for the u's. It was in Gaussian integral from the start.
You mean that you use Fourier transform for delta
Yes,
functions?
yes,
Okay.
exactly. So I have a q hat to enforce this definition for each mu, and then I do my u integrals, which are still open. The u's are contained in this object. I do the u integrals. I get another this is a Gaussian integral, and I evaluate the Gaussian integral. It gives this matrix with the matrix R, which has this structure. Again, a tuplets matrix which has this structure that the Fourier transforms of the true autocovariance functions are involved, and these weights q hat mu are, however, exponentially distributed independent random variables. So we are now having the problem of, if we want to evaluate that, we need the spectrum of a certain random tuplets matrix. And this is what we expect, what we're actually doing. So you do that again, fingers crossed. I mean, this is not very clearly. We haven't been able to show actually that this decays as a function of the distance of the indices k and l sufficiently fast to be in the tuplets regime. So there's another case in the Segel regime. So there's another case where if things really go wrong, it would be a point to go back to. So let's do it blind, with autopilot. what you find is you get this expression for the R matrix, which depend on a set of momenta with spacing 1 over n rather than 1 over m, and the couplet and this object here is a sinc kernel, which many of you have seen, which is sharply peaked around the value p nu. So then you do again the same. You enforce the definitions of the R nu with delta functions using Fourier representations. You get an integral of this form. There's still an average in the end to be performed over exponentially distributed Q hats. Then if you stare at this, you find that you can do the R integrals using residues, and you get an equation of this form. So it's an expectation of a product under the conditions that I'm allowed to use Segev's theorem in the places that I've done. This is still an exact expression. However, what you find is that there's these F nus. They contain, of course, these random Q nus. This S kernel couples many of them. So we suddenly have a fairly complicated result, and here we actually have to do very rough things. So looking at this S kernel, what we basically say, we approximate the sum by replacing this complicated S kernel by a rectangular window of width 2 over alpha. This is an act of desperation. I'm sorry, but we tried many other things. It's just a too complicated.
So it's not parametrically justified.
No.
It's just your intuition that they should give
It's
leading contribution.
It's the intuition that it should give the leading contribution,
But
and it's
the
the
question is
intuition
leading in what parameter?
in small alpha. At small alpha, you
Okay.
expect that actually to be a rather good approximation.
So
Yes.
for small alpha, it's
Yes,
controlled.
yes. That's in small alpha, it's controllable. So this is the first approximation. The next thing, we replace the average of the product of the F's by the product of average, which again is a decorrelation approximation, which is very difficult to justify quantitatively. So yes, bear with me. This is it's just the thing is, yeah, we have to be, because actually my first result was much cleaner but wrong. It used a saddle point. It's used a saddle point evaluation. We cannot use saddle point evaluations of these integrals. So we really have a proper field theoretic problem here, which we have to solve. And as they are, if they are not Gaussian, as you know, they are just notoriously difficult. So yes, it's bold, it's autopilot a lot. But if we do that, this is our result for this average of the partition function. It's a product. And so it's easy to take the logarithm of that, and in the limit of large n, these p nus are dense. The sum can be substituted by an integral, and this is the result. This is the result which I announced earlier. So the structure of this is obtained by several acts of desperation, and clearly it's now an issue whether we are anywhere near the truth. And the interpretation we did already, if we have C hat of Q identically 1 for uncorrelated data, then if you look at this formula, rho 0 must actually be the spectral density for uncorrelated data. So, and this is a structural theorem which we believe to be true, and everything points it from the results, which I will show now, but we don't have a proof yet. So here is actually the case for IID data. So what you see is in green, greenish, yellowish, is a simulation for alpha equals 0.1 using matrices of dimension 1000. I forgot how many samples, kind of 2000 or so. The red curve is our approximation for the spectral density, and you see it's clearly not exact. The blue curve is the corresponding version of the Marchenko-Pastur law at the same at the same aspect ratio. That's clearly further from the truth. And actually my first saddle point results had the Marchenko pass-through law in it, which was beautiful, and I thought it couldn't be wrong, but it is. So
But it is, yes, not that bad.
it's not that bad. The nice thing is now let's come exploiting this, and we exploit this under an integral, and there may be some cancellations of errors. And here's an example. So we take, for example, an autoregressive process at alpha equals 0.1. Here's again the scaling function, though, so the uncorrelated data now plotted as a function of logarithm of lambda, because the spectra are fairly broad. Okay, the green is the simulation, the red is our analytic curve. And on the right, you see that our prediction, you see a simulation in green, you see in red our prediction for the spectrum, and you see in black the prediction that we would get using this green curve. And they are all basically on top of each other. So despite the fact that we did fairly rough things on the way, it looks as if our result is pretty good. So let's see what happens if we deliberately make our data situation worse by going to larger alpha. Alpha equals 0.8. Then this big saddle here, so first the scaling function becomes broader, and on the right-hand side, this is the spectrum at larger alpha for the same process. It has a totally different shape, and our scaling result allows to predict what the change to the shape is if we change our alpha, which is, for a data analysis problem, is probably something which might be useful.
Alpha is not small.
Sorry?
Alpha is not small anymore.
Alpha is not small anymore. Alpha is not small anymore, but you see, of course, if you zoom into this, I can probably even do that.
So in the tails, it's
If I zoom into the tail, you see that there are discrepancies. What you always see is that the green curve is on the black curve, and the black curve uses the numerically determined white noise spectrum. And that's what we always find. So the suggestion from our numerics is that our scaling expression is indeed exact. Our result for the scaling function is not, sadly.
but still surprisingly nice.
Still, it's given that we were forced to make really badly controlled approximation at least twice. So here's a case where it's an autoregressive process of order 2, where the shift operator has 2 real eigenvalues, and this is not giving you again the scaling function. This is the alpha equals 0.1 case, and this is the same spectrum at alpha equals 0.8. The shapes are totally different, but we predict the different shapes. If you take an autoregressive process where you put the parameters in such a way that the shift operator has 2 complex conjugate eigenvalues, then the left is the spectrum at alpha equals 0.1, and you always see 3 curves, a black, a green, and a red. The red is our analytic prediction, black is prediction using the empirical scaling function, and green is simulation. And this is at alpha equals 0.1. And these are, in principle, the spectra for the same stochastic processes. And this finally is a case which, in power law decay of auto-covariance functions, this decays to like 1 over n squared, so it's in integer powers, it's just about absolutely summable. And then you here also see green, black, and red. It's fairly noisy on the black. The reason is the following. The Fourier transform of C bar for this thing produces very small values. And if you recall the scaling function, the scaling result was an integral dq over pi 1 over c hat of q rho 0 over lambda divided by c hat of q. And if you get small values of these, then you go into the tails of the distribution where our data situation is bad, and then you even amplify it. So that is something which creates the fluctuations. But our analytic result is not really far off. There's only slight differences, really, again, in the tails. We can use our analytic results even in this case with power law decay, so very strongly correlated random variables. And that's about it. Let me summarize. So what we've done is we computed the density of states for sample autocovariance matrices. It's in fact, as we get it via a multiplication of a Hankel matrix, which is with its transpose. In effect, what we are doing is we compute actually a singular value decomposition for a rectangular Hankel matrix. The key ingredient in the calculation is using Segers' theorem for spectra of tuplet matrices twice. In one case, we're pretty sure that we're justified to do it. In the other, not as sure. And then we have these two really rough and uncontrolled approximation, which we were forced to make in order to get anywhere. But it appears that we are luckier than we deserve in the final result. We obtain, using this scaling form, it amounts to a generalization of Segers' result to the case where we have sampling noise. Our numerical results clearly suggest that this scaling result is an exact result, which we haven't been able to prove. We've tried several ideas and always run at fairly hard walls. I thought I had made progress these days, but I'm not so sure anymore. So this is a very volatile situation. I believe it should have plenty of applications in time series analysis, signal processing, in finance, and so on and so on. And finally, I should thank these three guys. The entire problem was started or triggered by a discussion with three postdocs then at Trieste, Kartik Anand, Luca D'Allasta, and Pier Paolo Vivo. And that's what I have to say. Thank you for your attention.
So there were plenty of questions. Are there any further questions or comments?
Impressive. Impressive, yeah.
But non-rigorous.
It's not clear why it works.
It's not clear why
Clearly works.
Well, I mean, it's not entirely unclear why it works, but it clearly works better than we deserve.
Yeah, the approximations are very striking.
Yes. There may be room to. I mean, this one-dimensional model. Maybe there may be techniques to improve on that. But it's tough. It's tough. It wasn't. I mean, it took a long while to get there. We had many false attempts, as you might imagine.
Okay. Right. More comments or questions? Okay, let us thank the speaker again.